Welcome everybody to Organic Chemistry, new unit. There's going to be a lot of drawing involved, so I apologize in advance for how messy it's going to look using this method, but we're going to make the best of it. So organic chemistry, we're going to be using reference tables P, Q, and R. Not all of them in this first section, but you might want to get that ready. As well as periodic table. So make sure you've got your reference table. We will be doing some drawing in a little bit, so if you want to follow along, pencil or pen. So first of all, what does it mean to be organic in the first place? Like, I know everybody goes to the produce and you'll see there is organic produce versus, non-organic, and the organic stuff costs more and it kind of looks the same, but that actually doesn't have anything to do with the chemical definition of organic. Organic means containing carbon or carbon compounds. So the organic process for foods has to do with pesticides and the procedures they use in the growing or the harvesting, not really involved with this at all. So we're going to take food off the table and we're going to focus solely on our chemical elements. So organic chemistry is an ever-evolving field because it is able to really evolve. There are so many carbon compounds because it offers such kind of flexibility here. Now here's just, and again, I apologize that we have that screencastify image at the bottom, but you'll notice that carbon chains can be very, very long. And that's a very unique property of carbon, is that it can form long, long chains. How long? Well, in the thousands to practically innumerable. It can also form rings and networks. So let's keep going with that. So we talked about in solutions what it meant to be saturated. So in solutions, saturated means we have the most dissolved solute. In organic chemistry, that has nothing to do with dissolved solute, but it does mean the same as the maximum. So saturated compounds have the maximum number of bonds. So bonds to different things. Now, go to periodic table. Here I am, I'm going there too. Go to periodic table, find carbon. How many valence electrons? Valence electrons, there are 4 valence electrons, which means carbon can form 4 bonds. In a saturated compound, carbon is going to have all single bonds, so there's going to be 4 different 4 bonds with different elements, different atoms. So for example, we would consider this a saturated compound because it has all single bonds. They are saturated. That's another way I remember is saturated is single. So we look, this leftmost carbon has 1, 2, 3, 4 bonds to 1, 2, 3, 4 different atoms. Same with the middle one, same with the rightmost one. So saturated compounds have all single bonds. If you have a double or triple bond, that's not going to be 4 different atoms. That's going to be maybe 3 atoms or 2. So we would call those unsaturated. Unsaturated have either a double bond or a triple bond. Thankfully, that didn't disrupt our pictures here. So notice again, carbon's always going to form 4 bonds. That doesn't change. But instead of this one where we had 1, 2, 3, 4 different atoms, in this one, take a look. We've got 1, 2, 3 atoms that it's bonding to. There's a double bond within these 2 carbons. So we'd call this unsaturated because there we have a double bond. This is a good time to remind ourselves. In a single bond, we have 2 shared electrons. In a double bond, we have 1, 2, 3, 4 shared electrons. Over here, we have a triple bond. That's 1, 2, 3, 4, 5, 6 shared electrons. So if you look over here, this is called a triple bond structure. Carbon always will have those 4 bonds, but instead of being to 4 different things, it's only going to be to 1, 2 different things. These are called unsaturated. So carbon compounds can be saturated with all single bonds, or they could be unsaturated with multiple bonds. Here's some review. We've talked about the kinds of formulas. We've talked about empirical formulas, which are the most simplified form. We've talked about molecular formula, which is not necessarily the most simplified. So the actual number, C3H8. I could even say C4H8. Why not? It is some multiple larger, okay? It can be simplified down, it might not, but in this case, it could be simplified down, so it's definitely not an empirical. In organic chemistry, we are focused on structure. So the formula type that is most important are called structural formulas. So structural formulas are not going to be, we group the carbons together, we group the hydrogens together. We're going to show how they are built. And the structural formula is going to allow us to figure out chemical properties later on. So for example, and I do apologize because of this being here. For this example, we have 3 carbons bonded such a way. If you notice, I'll get rid of this now. C3H8, we have C3H8. That's wonderful. But a structural formula is going to show us how it's put together. So we read from left to right. We have a C. What's bonded to that C? 1, 2, 3 H's. Then we have another C. What's it bonded to? 2 H's. Yes, it's also bonded to this, but we're just going to let that go. And then we have another C. What's that bonded to? 1, 2, 3 H's. And of course, I had that there, but I wanted to show you. So this, although it takes more time to write, although it looks like it's kind of unorganized, it actually is very important to show us how to draw it. Because if you see this, it's kind of like, what do I do? But this is a road map. A road map to drawing, that's a P. Road map to writing and drawing. Structural. All right, let's get our reference tables out. Let's go to table Q, please. Table Q. I'm gonna let you get there. It's on table Q, page 7. So table Q is the homologous series. Remember, the prefix homo means same. So these are groups of the same. Notice there are 3 kinds of homologous series. We call them the alkanes, the alkenes, and the alkynes. So before we go any further, what is a homologous series? This is a definition that's kind of wordy. They are just related compounds. That's a lot. I don't know that I love that formula. But these are called homologous series of hydrocarbons. What is a hydrocarbon? Well, take a look at those pictures. I see hydrogens and I see carbons, and I don't see anything else. So that's why it's called a hydrocarbon. These are organic compounds that contain only hydrogen and carbon atoms. We sometimes call these the parent compounds because a lot of the other organic compounds we're going to study are derived or come from them. So these are kind of like the backbone, and we can attach other things later on. So if you're looking at table Q, you see we have 3 different kinds of homologous series. Just take a look at them right now. So I'm just looking at what we call the alkanes. Alkanes have all single bonds. If you look at alkene, you see a double bond. If you look at alkyne, you see a triple bond. So that is important. So it has to do with the kind of bond you find. So alkane, single bond. And you only need 1 double bond and you're an alkene. So double, alkyne, triple. All right. So are they saturated or unsaturated? Well, if you are saturated, you're going to have all single bonds. Unsaturated means you don't have all single bonds, which means both of these. A general structural formula. Okay, so because we can have as many carbons as the world is large, we need a generalized way of writing an alkane. So if you look on table Q, the general formula for an alkane is CnH2n plus 2. What is N? Look at the bottom of table Q. N means number of carbon atoms. So for example, let's say I have 5 carbon atoms. So if I have C5, how many hydrogens will I have? This is just a little bit of algebra. So 2 times 5 is 10, plus 2 is 12. And you know what? I shouldn't have chosen so many carbons. 1, 2, 3, 4, 5. I know how many hydrogens there's going to be. There's going to be 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Boom! I was right. The general formula helped me. Oh, by the way, do you see how I didn't draw any H's in here? Stay tuned. Now take a look. Look at the general formula for an alkene. It's just double the carbons. So let's say I have 2 carbons and I have a double bond. How many hydrogens will there be? This is 2. This would be 4. 1, 2, 3, 4. I was right. And then an alkyne, if I have 2 carbons with a triple bond between them, I should have 2 times 2 is 4, minus 2 is only 2 hydrogens. Oh, look, that's right. Sorry, that's so messy. So these general formulas are super helpful. They will tell you how to draw it, because before you even start drawing, it'll tell you, hey, am I right? So alkanes, I think you might be the most familiar with. These are the things that we use to burn. These are the things we use to create energy or use the harnessed energy. So propane tanks or methane or octane in gasolines. So these are the things that we burn. Hard to see here, I apologize. If you increase the number of carbons, so the more carbons in your alkane, the higher your boiling point is going to be. We'll talk about that later also. So we're going to learn that methane has 1 carbon and octane has 8 carbons. Octane would have a higher boiling point because there are more carbons. So alkenes and alkynes. We don't really talk about these too much, but alkenes, these are kind of like the starter materials to make other things like plastics. Alkynes use ethine for welding torch fuel. I have never seen a Regents question asking you about that, so I wouldn't stress too much, but I would focus on the alkanes. How are we doing? Do you want to take a break? Want to press pause and go pet your cat or grab a sparkling beverage like a LaCroix? Maybe not? I'm going to keep going. Can you tell I had some coffee? I had a little bit of coffee. All right, this is review. Isomers. Isomers are super important in organic chemistry. So isomers have the same molecular formula, so same number of atoms. However, different structural formulas, which means different arrangements. Okay, so if I gave you 10 Legos and I said, build something, you could build it. Then I say, take it apart. Build something again using those same 10 Legos. You could do it and it would look different. So you use those same pieces, but you're just putting them together in different ways. That's isomers. So the same atoms, just rearranged. And so, of course, you know, if we have different structural formulas, we're going to have different physical and chemical properties. The way things are put together will allow them to react differently. So let's take a look. We have C4H10. So before we go any further, alkane, alkene, or alkyne? How do we know? All right, I'm going to take a look at table Q. I notice that N is 4. So we have 10 hydrogens. So if it's an alkane, 2 times N, which is 4, would be 8, plus 2 is 10. This is an alkane. Very good. Thanks. All right, so here are 2 what we call isomers. Notice that both of them have 1, 2, 3, 4 carbons. There we go. And 10 hydrogens. 3, 6, wait. 5 and 5. Good. All right, just trust me. So let's draw these according to their structural formulas. Are you ready? So we start with a CH3. C, H's. Good. CH2. C, H2. That's an H. Just trust me. C, H2. C, H3. Now, later today, you're going to learn how to name that. But for right now, I'm going to tell you meth, eth, prop, but. This is butane. All right. This is a different way of drawing and putting them together. CH3. Wait, I don't know how to draw this. Where are you getting this structure? Don't worry, we'll get to it. CH3. Ooh, that would end my chain. Hold on a second, you. I'm going to go beyond. CH. Let's have this be the CH. CH3. And then here's my CH3. Wait, I'm confused. I don't know what you're doing. Relax. CH3, CH3, CH, CH3. This is called methyl propane. I don't know how to name that. Don't worry, we'll get to it. Now notice how because they're put together in different ways, they're going to have, oh, I had that written, oops. They're going to have different boiling points. So I'm just showing you that the way they're put together definitely matters. All right, here we go. Let's get out reference table P, Q, and that should be it. So let's take a look at table P to start. So on page 7, table P. Those are called organic prefixes. A prefix, it comes before the word and it will describe it. So if you see, we have prefixes meth, eth, prop, but, pent, hex, hept, oct, non, and dec. And that will tell us the number of carbon atoms. So if we have a 1 carbon atom compound, we'll call it meth something. So the ending is something that is going to change. But if we have 1 carbon, it's going to have meth. 2 carbons, it's going to be eth, 3 prop, etc. So we're going to start by what we call straight chain hydrocarbons. So just a straight chain. The first thing we need to do is find the longest continuous chain of carbons. We call that the parent chain. Okay? The next, count your number of carbons and choose the appropriate prefix. So, like I was saying, let's say we have 6 carbons. It's going to be hex something. What is that suffix, the ending? Well, this is where the kind of bonding comes into play. If you have all single bonds, like, one of those alkanes, we end it with ane. If you have at least one, gotta have one, or more double bonds, it's going to be ene. If you have at least one triple bond, it's going to be ine. So if we had a 1 carbon chain, all single bonds, it would be methane. Okay? Take a second to kind of take that in, and then let's give it a try. Make sure you've got table P and Q ready to go. Oh, and before we go any further, carbon can always form 4 bonds. They don't have to be 4 bonds to 4 different things, but they always have to have 4 bonds. How many bonds can hydrogen form? That's right, 1. Okay, so give yourself some space. If you're in the notes, take a deep breath. Here we go. CH4. See? 1, 2, 3, 4 bonds. H, 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 H. Table P, 1C. This is the example I just used. So 1 carbon is going to be meth. Notice how they're all single bonds. Ane. Good. Okay, this is going to be challenging for me to draw, but I'm going to do my best. CH3. H, H, H. And I sometimes put a check mark to say, hey, I did it. CH2. C, H, 2. Check. C, H, 2, check. CH2. Make sure yours look neater than mine. And CH3. Okay, great. So now we need to name this. 1, 2, 3, 4, 5 carbons. Go to table P. 5 carbons is the prefix pent. What kind of bonding do I have? I have all single bonds. Single bonds are saturated, and those are alkanes. So I end it with ane, pentane. All right, doing great. I can tell. CH to CH. I'm going to start with my 2 C's. I have 2 carbons and 2 hydrogens. So obviously I'm not going to have all single bonds here. So if I have a C to an H and a C to an H, that's not going to be good. That's not enough. What if I do a double bond? Carbon only has 3 bonds. Can't do it. I have a triple bond. Good. That's what I want. Also, you could have used table Q, noticing that if there's 2 carbons, then I would have 2 times 2, which is 4, minus 2, which is 2. So the same. Let's name this. 2 carbons is called F. Triple bond is an alkyne, ethine. Okay? Okay, try this next one. It's going to be a little weird. CH3. You know what? It is so challenging to draw these H's. I'm going to let you in on a little secret. You don't have to write the H. You always have to write the bond, but you don't have to write H's. It is understood as organic chemists, which you now are. So this is going to have an H. We just don't write it. Okay? So as long as we're in agreement, you know there's an H there. You do not need to write it. Okay, so we've got CH3, CH2. Oh, so check. C to an H. Okay. C to an H. Okay. And CH3. Let's make sure I did that right. CH3, CH2, CH, CH, CH3. Okay, I did it. But you should notice some gaping holes here. Something's wrong here. I don't have enough bonds. What does that mean? Should I throw some H's on here? No, it's not part of our structural formula. I might not have all single bonds. I might have a multiple bond. What if I do this? Then it works. Now this carbon has 4 bonds. This carbon has 4 bonds. Great. So now we're good. So the last thing we need to do is name this thing. 1, 2, 3, 4, 5 carbons. That's called pent. Double bond here. So that's an alkene. So this is pentene. So it's pretty unique that we have something like this. So we want to give it a location. So where is that double bond located? Well, I will tell you the rule. You always tell the location after the lowest number carbon. What do I mean by that? Well, I can count 1, 2, 3, 4, 5 carbons. This double bond comes after the 3rd carbon. But wait a second. What if I were to number it this way? 1, 2, 3, 4, 5. Now the double bond comes after the 2nd carbon. We're going to call it 2. Remember, folks, this is not etched in stone. These things are rotating around in space. If we were together in class, we would build this. So you can see that you can read it either way. So we call this 2. That is the location of that unique structure, pentene. All right? The last part. What if we have a branch? You know what? I think I'm going to make a separate recording of this. So I'm going to stop, and I want you to take a break, go take a walk, and then we'll come back. I'll do a separate recording for branches. Discard.